Swayam Prabha. Digital India. Educated India.
We're going to talk about a particular visualization technique called ISOM, where SOM stands for self-organizing maps, and the I part was developed by us. So the I here stands for interpretable. So I'll just go over the SOM and the ISOM part and what is the need for this, and Dipanshu will demonstrate a particular technique that existed without the ISOM component. It's called Pareto-Race. There are other techniques to visualize your multi-objective Pareto front, like Nimbus, and there are other competing techniques as well. So we used this ISOM component in Pareto-Race and demonstrated how it can be useful while navigating a Pareto surface, especially in higher dimensions. So this will be the flow of the content. We will introduce what is the need for visualization and optimization type of problems and ISOM. Then Dipanshu will take over to demonstrate ISOM plus Pareto-Race. This probably most of you sort of understand this part, but for the sake of completeness I show this slide. Today design by default is simulation driven. We go to the experiment table much lesser times compared to what we used to do several decades ago. I remember about 30 years ago when we used to present finite element results, we also present a calibration slide. We just show a cantilever beam, we know PL cube over 3EI, and we also solve the same problem on FEM, and then we show it's calibrated, right. Today we don't show that because finite element is accepted. So is the case with Simulink or CFT simulations and stuff like that. So all these images or GIFs are borrowed from an industry partner, but the reason that we have this here is that any of this simulation is super expensive from the time perspective. Okay. If you have to solve a car crash problem, like a high fidelity problem, it's in our high performance computing facility, it's going to take like 16 hours overnight. It's not on your desktop. Okay. If you're going to use a high performance computer, it takes about 16 hours, which is overnight. Right. So if you want to do a modal analysis and understand the several modes, that is also expensive. And the interesting point to note is, it is not sufficient if you just do one. You'll have to do multiple design combinations, you'll have to visualize, and visualize in the sense you'll have to look at the results. The second part is optimization by itself is expensive because it's iterative in nature. Right. So there are some design variables, you'll have to go check what your objective function is, what your constraint is, whether it's violating or not, and then you find the derivatives, or you use a evolutionary algorithm type, and then you come back to the next set of design variables, and then we keep solving it in an iterative fashion. So if we use these models directly, this is going to be super expensive. There are additional stuff on top of it. If you take it, look at it from a design cycle perspective, overall we are talking about 3 to 6 weeks, and your simulation time can be anywhere between 2 to 120 or sometimes even more than that. For instance, the virtual wind tunnel test takes about 4 days. Okay. But then you don't have to build the wind tunnel. But one simulation takes about 4 days and nights to solve. The interesting point in this whole stuff from optimization perspective is there is a lot of input output data that happens with respect to the iterations. Right? However, after you find the optima, somewhere close to 95 to 98% of these points or information is discarded because we focus on the optima. He also multiple times during his lectures he pointed out it is not enough oftentimes if you just find that one optimal point. Instead, it makes a lot of sense to designers to explore the design space, because when we generate some design combination as an optimal design combination and hand it over, they figure it out that they cannot manufacture for that design variable combination. There could be some limitations. Okay, maybe the gauge thickness is not available. So if you practice engineering in general, for instance, gauge thickness is available only as 12 or 14 mm. So if you generate 12.6 mm, unless you are Tata or Birla, you cannot manufacture that. Okay, if you are going to take something off the shelf, it's either 12 or 14, and 14 is something that they are already doing. So what it means is 12.6 does not make sense to them because they cannot manufacture that, right. So now the question is, what do? I cannot manufacture 12.4 gauge. So then you'll have to go back and run your optimization algorithm again with this particular constraint. Instead, if you are able to visualize the design space that says like, okay, this is an optima, but I can't achieve these design variable combinations. So what might be the next best stuff? And then there are also other considerations like robust design. What it means is, irrespective of your variability in the input space, you want your output variation to be less. So you want to identify these kind of design combinations in your space. It is interesting to explore the design space, especially in a visual sense, if it's possible. The challenge with visualizing the design spaces, usually it is higher dimension. When I mean higher dimensions, I mean like greater than 3 dimensions, right? Because greater than 3 we cannot visualize as of now unless it's a projection, and projection only gives you part of the story. It doesn't tell you how the other variables vary in the other dimension. So simultaneous variation of the variables are not captured. So that is essentially the thrust for our research or work here. And why we are interested in looking at the design space, not just the numbers, visualizing the design spaces. If you look at all the simulation results that I showed here, these are all actually complex physics from a physics perspective. Okay, there is a fluid structure interaction, there is a CFD simulation, there is a contact mechanics problem. If you actually delve into the physics of these problems, these are super complicated. But you go to the industry people who solve these problems, they can explain this like a cake to you. It's very simple for them. The analysis is very complicated, but they can explain this and they understand these results very nicely. So it took us a while to understand then how come the math that we introduce them to, for instance, meta model building or evolutionary computation or any kind of optimization math, is relatively difficult for them when they can do all this stuff and are able to explain the physics behind it looking at this. So the part is looking at it, right. So they are able to see these results and it leads to intuitive decision making. Whereas if you just present data, which is what we are actually doing in optimization, right. So whatever you looked at, he demonstrated the Pareto friend, he gave you examples, everything we were able to see in 2 objectives. The moment he increases the objective to 4 or 5, we cannot see that front because it is going to be in some hyperspace. So the question was, if we can visualize that in higher dimension, then probably we also might be able to do intuitive, or maybe able to take intuitive decisions there as well. So that is the motivation. So I just step one step backward and then look at this as a generic engineering problem. Just like any engineering problem, we are also interested in y equals f of x, right. So oftentimes in a design context, you may not know the bounds of x. So you may not know the combinations of x. So you are just only going to have the bounds of x. So here, for the sake of discussion, I have x1 to x2, but it could be a vector here, right. And then we don't know the relationship between y and x, which is actually f. So that is something that is required. If you have the f, half of the game is over. So you can directly perform optimization on top of it. You can have sensitivity information and all that. So then you may want to build this relationship to proceed further. That's what linear algebra is all about, right. So then what we do in that condition is we take something called a design of experiment. So you have some random set of points. So it could be uniform samples, but there are some demerits of using uniform samples. So usually it is a statistics driven random experiments, right. So LHS, Latin hypercube sampling, or Montgomery pseudo random samples is the typical stuff. So once you do this, generating these samples are not expensive, but then getting this analysis, which is essentially the y at each of these combinations. So for instance, if you are talking about an automotive design, this one dot here means one design combination, one geometry, okay. This could be a sedan, this could be a coupe, if you have put the variables that way, right. Now if you are talking about y as a crash metric, then you are going to crash one car. So if you are looking at a BMW, we are talking about 50 lakhs for BMW, right. It's not the cost on the road. So then what happens is, if I just have 4 dots here, I am talking about 2 crores just from a test perspective. Okay. So the overall idea there is to minimize the number of points, but at the same time explore the entire design space as much as I can, so that I can maximize the information that I have. So once I have this, Okay, so it may not be like 50 lakhs because we are not going to necessarily crash it physically, but we are going to crash it on the computer. So it's few lakhs out there. The point is we don't have as many samples as we would like to. So we might want to minimize the number of samples. At the same time, we want to maximize the information with respect to the characteristics. So at each of these dots we or the sample, we generate the response, and once you have that, you have a set of X and you have a set of Y, and then you can figure out the relationship, right. So that's where your machine learning techniques or other approximation techniques like Kriging, radial basis function and all that come into picture. So now I have these input combination and then the F that is constructed. Once this is done, we can do optimization because you have an explicit function F now. So whatever you have studied in the last 3 days, 4 days, you can directly use this one, right. However, this itself is a chicken and egg problem because you don't know anything about the F before you build it, and the F is only as good as the number of samples and the fidelity of the responses that you give. So how many samples to use? You need to have some information about your F. So this is a chicken and egg problem, and typically done in an iterative fashion. Okay. The other thing is, if we go past that, then once you build the F, then you can do sensitivity analysis or optimization, whether it is deterministic or non-deterministic, which means you want to do reliability or robust design kind of stuff. And visualization also can be done from a decision perspective. Then on top of it, if you want to propagate uncertainties, so far we have only spoken about deterministic sense. At a couple of instances, he spoke about robust combinations or reliable combinations, right. So then what happens is the entire framework can also be replicated from propagating an uncertainties perspective. You first need to know the randomness, you need to know how to quantify them, then it needs to be propagated, then it needs to be analyzed. That's just for the introduction part. Now with this background, we are now convinced that we want to explore the design space, we want to visualize the design space, right. So what are the existing visualization techniques and what are their limitations? So these are some techniques. For instance, this is called a nested axis plot. This permits you to visualize 4 dimensions in one chart. How does it happen? X1 is fixed at -2 and X2 is fixed at -2, and X3 and X4 are varying here in this type. Okay. Now similarly, if you look at this, X1 is 1 and X2 is -2, and then X3 and X4 are varying like this. From this plot, can you tell me where the minima of this particular function is? The contours refer to this. For instance, these values are somewhere around 1. So where is the minima of this 4 variable problem? We are interested in finding the minima. Yeah, so 0, 0, correct. So if you just visualize from a visualization perspective, you see wherever it's dark blue in color, which is what is the minimum value, right. So now the point is, this is 4 dimensions. Right. This particular approach cannot be extended for higher dimensions. Okay. Until 4, this is great. Now if you take this, it's a tile plot. What happens is X1 is fixed and then you vary X4, X1 is fixed, you vary X3, and then you keep doing this for X2, X3. What happens if it is for other combinations of X1 and X2? Then you will have to repeat this tile plot. And if I have X1 to 20, then this keeps building in the X axis and the Y axis, and you are going to look at either the lower triangular matrix or the upper triangular matrix. And it also does not tell you what happens if I am going to change X3, right. So fixing X1 and then I am varying X4, but if I am going to change X3, I do not know what is going to be the variation with respect to X1 and X3. That is a major challenge. Then this parallel axis plot is great. It is typically used in software like Tableau or business intelligence, BI and all that. The one that we are showing you here is a 4 variable case as X1 to X4, and there are about 20 realizations. And now as a designer, you will have to make decisions on the combination. Now you can see it's sort of like very difficult. This is one possible stuff that's happening. There are the software try to make our life easier. Now whatever I showed you here by the red line, you click on it, it will highlight that in a different color, and then it puts it in different clusters and all that, but still with more number of instances, this becomes really cumbersome. And then heat map again has sort of tries to give you a pattern, but for instance in this particular case it's X1 to X10 and then F1, F2, F3 are the objectives, and if you are interested in particular combinations, then it becomes really difficult. And Radwis plot Professor Deb has worked on this. It has a very interesting physics concept behind it, and TSNE is predominantly used by computer scientists from a clustering perspective. I am not getting into the details. So, the point here is all these techniques are great, but there are some limitations. For instance, these are like 4 to 5 dimensions, this becomes cluttered in no time, and this is not for individual outcomes. Generally sort of trends try to give you a trend thing, and there is something called a clumping, and many to one, many solutions are sort of pointed to one. That is one thing, and several uncertain features. You have some tuning parameters in this, and there are some limitations. So, what is desired here is we might want to come up with an approach that lets you visualize the space. One thing is like the dimension. So, you cannot say it should be like 4, 5, whatever is the number of dimension, it should be able to scale relatively easily. And oftentimes in optimization, we might want the region of interest. So, it could be the feasible space, or it could if you are going to relax a constraint, if you are going to make it more stringent, what happens to your objective or your feasible space, these are the stuff. So, those are the regions of interest that you need to understand, and more importantly the relationship between your x and y, and sometimes the relationship amongst your x's also we might want to capture. So, we started using the self-organizing map. Self-organizing map itself is not our work. It was done by someone called Conan about 30-35 years ago, widely used by computer science people. This is essentially a artificial neural network. Right? The one feature that we are trying to leverage is it is very good in preserving the topology, meaning if there is an underlying function, and let us say your data is good enough to represent that function, this can build that function very closely. And importantly, if there are 2 points in the real function that are next to each other, in your approximation also they will be next to each other. That is what is the topology preservation part. And it actually lends itself very well because it can directly work on samples, because that is what you have like data, and high dimension it can scale. As far as the method is concerned, there is no limitation. Oftentimes people ask us, can it go to 200, can it go to 300? Yes, it can go to 1000 also, it is not a problem. But again, what will you do with 1000 variables? Like, can you visualize 1000 variables? That is the other discussion that comes up. But from the method perspective, it can do. From the math perspective, it can do any number of dimensions. That is not an issue. How does this work is, if you just go back to our design of experiment point, because I am just explaining it from the big picture perspective. You have a set of points on the design of experiment, and each point is mapped to a layer in the ANN, right. So, the only difference in the general ANN that you might do is this includes the input combination as well as the output. So, if I have like 10 points, I am going to have 10 layers, okay. And then this is our net that I am talking about. Generally it starts with a uniform check, like a net supposed to be uniformly placed, okay. These are the nodes that we are talking about. The whole idea is to train these nodes to fit into the underlying function based on the data that you have. So, this happens over an iterative fashion. It is actually a regular weighting stuff. There is also some learning function and decay stuff that we use, and after that it takes the shape of this. For instance, you start with this sort of a nodal layer, and then you go to the original function or whatever based on the data, whatever that layer is. Right. Now, how do I interpret the SOM outcomes? For the sake of discussion, we have this bowl function. We call it the bowl function because it looks like a bowl, x, y and z. I have this bowl function so that you appreciate it, but we do not need the bowl function. All we need is the data. Imagine that I have 20 x, y and z. You can subject it to, we call the conventional implementation as CSOM and our implementation as ISOM. Now, we will first look at the CSOM. Okay, this some issue with the formatting. This is the Z part. So, when you take the 20 points and subject it to a CSOM algorithm, this is the plot that you get. How do you interpret these plots is, if you are interested in minimizing the Z, so you are interested in the color blue because that is where the minimum value is. If you want to know what combinations of x and y will give you the Z, you just have to go to the same coordinate here. So, these two combinations is likely to give me the Z. So, if you go back to this is sort of like yellowish green. So, that is around 0, same is the case here, that is around 0. So, 0, 0 is what it is going to give me the minimum value. Similarly, for any other combination I can do. The beauty here is, given z I can tell you the x and y, or given an x and y I can tell you what the potential z's are. So, this permits you to solve both the forward problem and the inverse problem. This is the advantage of graph based approaches like these, because otherwise if you are just going to build an approximation, right, I gave you x's, I gave you y's and I gave you z. So, you will build z as a function of x and y. So, if I give you a new x and y, you will give me the z, but if I give you a z, you cannot give me the x and y, because you need an f inverse, right. Whereas graph based approaches like this, they permit you to solve both the forward and the inverse problem. And there are other additional stuff that we can do. For instance, we can understand the relationship between x and y if there is any. Okay. Are they inversely related, or are they going to be similar in terms of their effect on the z? And for the sake of discussion, I am showing 2D, but it can extend to any dimensions, okay, which I will show in the next few slides. The one limitation with the conventional implementation is, this does not capture the functions topography if you look at it, right. So, because the functions topography, if it captures at the center of the z plot, you should have minimum value and it should increase in a linear fashion radially. So, that is where our contribution came. We modified the existing algorithm and it made it inherently interpretable. So, if you look at it now, you have as an outcome from the isom, you have a z plot where the function is minimum at the center and then it is varying in a linear fashion. See, mathematically this guy also captures the same stuff. From a visual sense, it does not capture how the original function looks like. So, that is where the contribution comes from the isom part. And then also your x and y are linear, obviously from an axis perspective, that is captured here in the isom part as well. Okay. Now, what actually we are doing, if you are really interested? So, the way this works is, there is something called a best matching unit. So, you remember the initial net that we use. So, this is the net that I am talking about, the black dots here, right. So, there are going to be points in space which is our data, and all we are going to do is do some distance computation, and then for a particular node which data is closest, towards that data the node gets dragged, and you go to the next point and then the next set of points will be searched and then it will get dragged. When they get dragged, the neighborhood points also gets dragged along with it. This happens for the entire set of points, and that is how the points or the initial mesh gets deformed into the shape based on the data that you have. In the conventional SOM, the point in space includes the outcomes as well. So, if you see here, this is the point that we are considering, because it includes the outcome as well. So, if I want to understand the distance, then I measure this as the distance for the conventional implementation. As a result of it, what happens is, sometimes these points will be picked up in a random sense. So, there could be something called bending, self bending or aberration, which will compromise the way in which you could visualize the original function, though the math is still preserved. Okay. From a visualization perspective, there is aberration, self folding. So, what we did is, instead of taking the outcome, we just compute the best matching unit based on the input, and after the best matching units are aligned, we just move the y axis or the z values, right. So, then we do not get this folding and we are able to identify the function. For instance, this is the folding that I am talking about. Okay. This happened in a CSOM case, whereas for the same set of data in the ISOM, it is like super clear, there is no folding here. Okay. All right. So, that is just, so with this we have been able to address a few stuff. The one stuff that I am going to talk about, which is also related to what we discussed here, is ND graphical optimization. So far you have seen that we can do optimization graphically using two variables, right. It is super useful, because if you want to explain Lagrangian multiplier kind of concepts or constraint violation and all that, it is useful to look at it in 2 dimensions. But what if we can do this in n dimension? You can't do in principle. If you are just going to use analytical approaches, you can't do it, because greater than 2 dimensions you cannot visualize. But with ISOM you will be able to do it. And the other thing that we will discuss is, Deepanshu will discuss, is the Pareto-Race MO kind of stuff, right. So, the state of the art is limited to 2D or 3D, but we could use ISOM to be able to do this in higher dimensions. So, this is a linear programming problem. Okay. Your objective and your constraints are linear, and if I were to plot this in an analytical sense, so this is your x1 and x2, and I am just plotting the constraints. and these are the infeasible space, this is the feasible region. So, if you know a little bit of optimization, you can even figure out where the optima is just from this plot. Okay. Now, what we can do is what happens if I am going to relax this constraint a little bit? You can immediately say the feasible space is going to increase. To some extent, you can even compare this space with that space and you can say by how much it is going to increase. All this can be done, right. It can also be done mathematically, but visually it is more appealing and it is intuitive for the decision maker. But the catch with these approaches is this can only be done in 2 dimensions. Now, what we are doing is I am showing you the equivalent of this in ISOM, but the difference is ISOM can also be done in n dimensions. So, first we will start with 2 dimensions. For the ISOM, what we are doing is we are plotting the constraints G1, G2, G3, and this is the infeasible space, this is the feasible space. Of course, the infeasibility is defined by this, wherever the values are greater than 1, we are just marking it as gray. Then what we do is we overlap this G1, G2, G3, okay. And then as you can see just from here, if I overlap these 3, I will sort of get something equivalent to this, which is what is this part, okay. This green dotted lines are equivalent to this space, but this is obtained through ISOM, this is by general graphing ideas. Okay. Now, the same idea, this is a 7 variable problem that we are looking at, x7, okay, and then there are about 4 constraints. There is no limitation, it can be 10 variables, it can be 20, 50, 100 variables, it can be 10 constraints, it can be 8 constraints, 50 constraints, does not matter, right, but you will have to plot those many constraints. If there were like 4 constraints, we have plotted 4 plots here, right. So, same philosophy, infeasible region, feasible region with contours. So, we are able to plot all this and all this is based on data. For instance, this for the sake of discussion we are showing you the equations, but instead of this equation you have a Funnel element model, let us say. You just run those model based on some DOE points and then you have the data, you can run these plots. Once you get that, we just overlap these 4 plots and this is what is your feasible region. And now, this is more informative for a designer because even if you want to run an optimizer, you do not have to search the entire design space because your result is going to be only in the feasible space. So, this is roughly about 1/4 of your entire design space. So, that is one thing. Or you want to know which constraint is going to be more effective. I will show you a slide where you can take a look at that, right. So, there are other additional stuff that you can do on this, right. This just shows that you can do an optima by just looking at it. We are trying to predict where the optima is going to lie, or at least can it be, can I bound the optima? It is possible. We took the same approach and then applied it to the car side impact problem. In our community, this is a beaten to death problem, but it is also a benchmark problem. So, it is interesting to solve this, right. So, we did the same stuff. There are about 10 constraints and 30 variables. No, 10 constraints. How many variables? 11 variables, okay. So, we get this and then we overlap all these stuff and this is what is our design space. I mean, sorry, the feasible space. Now, I have a question for you in this. Now, let us say I tell you that you can move one constraint because all these are constraints, okay. You can move one constraint, okay. You can move any of the constraint that you want, but moving each constraint is going to cost you 10 lakhs and your budget is only 10 lakhs. So, which essentially means you can move only one constraint. Which constraint would you move? Sorry? D. Oh, this guy? Why? That is it, okay. Because if you look at it, we overlapped all these constraints and this is the space that we got and this space is mimicked by G4. So, if I am going to change G4, whether I am going to reduce it or I am going to increase it, that will affect the feasible space directly, almost 100%, right. This particular part will not be affected, that is all. Sorry? G? G7 also, G4 is 1, that is why I just took this one. If you take this one, this is almost represents G7. G7 is going to be a subset of this subset, right. So, G7 100% it will affect, okay. So, G7, G4 they also have similar, actually you are right, actually it should be G7, it should be G7, G4 is the is a superset of that. So, after a while if you just keep increasing this, okay, let me take back what I told, it is actually G7, G7 is the one that will affect it 100%, right, and then this guy is going to be slightly bigger than that. So, if you are going to keep increasing this and then it hits here, then it will be larger than G4. then G4 starts playing a role. So, G7 is a key contributor or the key influencer with respect to your feasible space. You can also get this mathematically, okay, but then not in a single shot. Okay, you can plot all these things and then you can take a call from here, right? And then the second thing is, let's say we said, oh, we figured out that we have about 30 lakhs. So, G7 and G4 will affect what other stuff can we change, which will impact the feasible space the most, or if there are some other objective bounds that we have, then we can do it with respect to the plots that we have. So, these kind of decisions can be made in a single shot stuff. So, that was made possible. And okay, we are just showing here for the sake of academic interest, we are just showing what was the maximum shrinkage that you can get, what is the minimum shrinkage that you can get, and these are different problems, of course not discussed in this presentation, but if you go to the paper you have all these examples that we have discussed, right. And with this fundamental idea, you can do multiple things in an end-to-end optimization stuff, and the one thing that Dipanshu is going to take over will be the Pareto front visualization. Okay. Now, he showed you multiple times these kind of plots on the Pareto front, right. So, this was your F1 and F2, and then you can take decisions, and then this particular point cannot do any better than F1 without compromising on F2 and all that, right. Now, if this was another dimension also, you can sort of do this visually, right, but the moment it is greater than that, it becomes a problem, and even in this simultaneous variation is an issue. Now, what happens is for the sake of demonstration, I am taking three objectives here. It is a DTLZ problem. It is an interesting problem because it has a discontinuous Pareto front. You see here, it is a discontinuous Pareto front, it is not a continuous Pareto front. So, we are trying to see if ISOM can capture that and what design decisions can you make. Okay. Now, the way to read this is, I am interested in minimizing F1, F2, F3, right. So, if I am interested in minimizing F1, F1, I can be anywhere here because that is where the blue thing is, blue means it is minimum. So, with respect to F2, I can be anywhere here, and with respect to F3, I can be here. So, it is conflicting, okay. Between F1 and F2, this particular end edge might be fine, but then F3 is max in that edge. So, I am here or I am here if I am looking at minimization. So, that directly tells you that it is a trade off. Okay. Now, from this plot, can you tell me what could be the trade off point if you want to minimize all three of them? Just the region in the plots. You get the question, right? You can't be minimal simultaneously on all the three objectives. So, there is going to be a compromise. So, you can sort of compromise, which means compromise means it is going to be higher values for F1, but then there are different directions you can go in F1, F2, F3. But just looking at this plot, you can tell me what is the likely optima or what is the likely trade off. You can't go wrong, there is no unique answer, sorry, sort of in the center. That is an obvious outcome, right, but then it is a trade off. You do not have a blue in any of them, it is a yellow color here or, yeah. So, that is what, simultaneously all three, then there is, you have to compromise, that is the thing, okay. So, so you can do this in a visual sense, but let us say we go back to his point. He says, so what, only in F2 it is high, I am willing to take that, I am only very interested in F1 and F2, F3. F2 I am okay to take a little bit of a trade off, that is what the whole point of trade off is, right. Then maybe what he says is a potential stuff. So, you could probably select a design here, okay. And so is the case, you can also select other design combinations. For instance, here these two are minimal, but this is not. So, maybe F1 being higher is still okay for you, right. So, this, but how much is it going to be higher? You can compute all this from an algorithm also, but it will only give you numbers one at a time. But when you plot this in one shot, you will be able to look at this. All right. So, with that, I'll sort of wrap up my part of this discussion, and Dipanshu will take over, but between you and Dipanshu is tea. So, we will finish tea and then come back. Okay, the earlier you come, the earlier we finish. Okay, so when you go is in your hands. All right, we'll see you then.